Hello, welcome to Mekki Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement of creating these kinds of technical videos in public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me a spark of creating these kinds of technical videos in public domain. And I would like to thank Almighty my God for my good health and broad mind. And I would like to thank my friends, followers, my dear students and subscribers. Today's topic of interest is hydraulic turbines. First of all, the hydraulic turbines are used in hydroelectric power stations where a stationary reservoir called a dam is there. From the dam, by means of a penstock, we used to drag the water from a stationary potential energy into an kinetic energy of a turbine, and this pressure and kinetic energy is applied in the turbine for producing electricity. And after producing the electricity, after rotating the turbine is coupled with the generator, that is why it is producing electricity. After running the turbine, this high velocity and high pressure stream of water is used in the draft angle, the draft, by means of a draft tube, it is delivered to the overflow river. That is how the power is generated from the hydroelectric power stations. First, we would like to know what is meant by hydraulic machines. Generally, a hydraulic machine is a device which converts the hydraulic energy into mechanical energy or mechanical energy into hydraulic energy, like vice versa. The hydraulic machine is supposed to convert the hydraulic energy into mechanical energy or mechanical energy into hydraulic energy. This hydraulic energy to mechanical energy is converted by means of a turbine, where the mechanical energy into hydraulic energy is converted by means of a pump. So here the turbine is a work producing device and pump is a work taking device. It takes the work and produces a hydraulic energy. So that is the difference between the turbine as well as the pump. So here, if we want to study about the turbines, first of all we have to know what is the impact of jet. By means of an impact force, that is impulse momentum principle, by means of an impulse momentum principle, the turbines are being worked. So this is the important point you have to know. That is, the change in momentum of an object is equal to impulse applied to it. So this is the equation is derived from Newton's second law of motion or force law. It states that clearly F is equal to ma, where F is equal to m into a. We know that acceleration is the dv by dt. Therefore, that is v1 minus v2 divided by t, the time change. So, with this equation into m, that is called the force, the impulse of the force is given by the change in momentum caused by the force of the body. That is, when we say this equation m into v1 minus m into v2, so that is the impulse momentum, that is force into time. So this is the impulse momentum equation. Force into time is equal to mv1 minus mv2. So this is called initial momentum, this is called final momentum, So with this, the initial and final momentum, the force exerted by the jet is being calculated. So here the force exerted by the jet on the plate F is equal to, we know that F is equal to m into V1 minus V2 by T. Here mass by time, the mass by time is the mass rate of flow. We know that uh, m by t is the mass rate of flow, that is rho into q into v1 minus v2. So that is the formula for finding the force exerted by the jet. So these things you have to remember that before studying the turbine. Here, the impact of the jet, we know that it is working on impulse momentum principle. A fluid jet is a stream of fluid issuing from the nozzle with high velocity, and hence the high kinetic energy is being taken. When the jet impinges on the plate or a vanes, it exerts force on it. So this force is due to change in momentum. It causes the change in momentum. We say a blade is in stationary position, a high velocity of the stream of water is producing an impact on the turbine blade, so it will tend to move. The blade tend to move. Therefore, the initial momentum to the final momentum is coming to picture. So the force is being exerted. So these can be calculated, or these can be known by means of a theory. We have two conditions. One is the force exerted by the jet on a stationary plate and moving plate. In different conditions, we can calculate and we can know better the impact of force or impact of jet. In stationary plate, the plate is held normal to the jet. The plate is inclined to the jet when we use curved plate, as well as the moving plate. The plate is held normally to the jet, or plate is held inclined to the jet. Plate is curved. So this curved plate is used in these curved plates are used in all the three types of turbines, the three curved as well as somewhat inclined. When it held normal, curved and normal, it is in the Pelton, and curved and inclined, it is we used in Francis or Kepler turbines. So that we come in later. So here the types of the turbines, majorly it is classified into two types. One is impulse turbine and another one is a reaction turbine. The impulse turbine is worked purely on kinetic energy of the jet, where in the reaction turbine it uses both pressure as well as the kinetic energy of the fluid stream. That is why the reaction turbines are used for low head, high rate of flow devices, or medium rate of flow devices we can use, where the impulse turbine is used in high head and low rate of flow devices. So for the further thing, we have to know the heads produced by the turbine. We know that majorly two heads are available. One is a gross head, that is the height difference between the head race as well as the tail race. The total height difference between the head race and the tail race is the gross head. That is called HG, gross head. Gross head is equal to net head plus friction head. So that is the interest. So if we want to know net head, we have to minus the friction head from the gross head. Then we get the net head. Net head is the head available at the head available at the nozzle or a tail race. So that is the useful head. Net head is the useful head, whereas the friction is being have to be minused from the gross head. So that is our interest. And losses, uh, generally turbines are also having some losses: the head loss in pinstock, head loss in nozzle, hydraulic losses, leakage loss, mechanical loss, and generator loss. We know that the hydraulic turbines, the hydraulic energy is converted into mechanical energy, and the mechanical energy is converted into electrical energy, where by in the hydraulic energies we transfer liquid from the dam to the turbine by means of a pinstock. Therefore, head loss in the pinstock is there, head loss in the nozzle is there, and hydraulic losses and other head as well as potential and velocity losses are there. There may be we are using a pinstock, that is nothing but a pipes. In pipe there may be any joint leakages are there. After that, the turbine is a mechanical device which which are having a rotating parts. Therefore, the rotational friction come into picture, that is called mechanical losses. And generally, uh, the all the rotation but in the generator is not at all converted into electrical energy, since only a 40 or 50 percentage of the rotational mechanical energy is converted into the electrical energy. Another things are losses, that is called generator losses. So the next is the efficiencies. We have a four different efficiencies, and one is a hydraulic efficiency. It is the ratio of output, the runner output to the actual power supplied to the runner. So runner output divided by rho GQH. So that is the hydraulic efficiency. The volumetric efficiency is the how much volume is being supplied at the nozzle and how much volume is hit at the blade. The volumetric efficiency is generally being in 90 to 100 percentage of efficiency. So we take 99 percentage as a volumetric efficiency. The formula for finding volumetric efficiency is that discharge supplied to the discharge plus the hydraulic losses. Next is the mechanical efficiency. It is the ratio of shaft output to the runner output. So that is called mechanical efficiency. And overall efficiency is the shaft output to the net power available. So the overall efficiency uh, is the mechanical efficiency into hydraulic efficiency into volumetric efficiency. That is called overall efficiency. So these are all the turbine efficiencies with their types. We know that the specific speed is a independent variable. It is put in the x direction, and the efficiency is a dependent variable, so it is in the y direction. We know that we have three types of a turbine: Pelton, Francis, and a Kepler. So Pelton turbine, it is, since it is a high head and low rate of flow, the efficiency is very limited. And the Francis is the medium rate turbine, and the Kepler is the high range turbine. Therefore, the efficiency, so these two things are the reaction turbines. This is an impulse turbine. Generally, the impulse turbine are uses very low rate of flow. Therefore, the dimensionless specific speed is very bit lower for the Pelton turbine. For the reaction turbine, it is medium to high end. The axial flow turbines are having a more specific speed and produces more efficiency in long range. So that is the interest about this turbine curve. Again, the types of the turbine according to the type of energy used, impulse and reaction, according to the direction of flow through the runner, that is tangential flow. The impulse turbines using tangential flow, and the rest of the flows are used in reaction turbines. The radial flow turbine, axial flow turbine, mixed flow turbine, or certain turbines. It is divided from the reaction turbine. According to the head at the inlet, high head turbines. Generally, high head turbines are impulse turbines, and medium and low head turbines are reaction turbines. And according to the specific speed, low specific speed is an impulse turbine, medium and high specific speed is a reaction turbine. If you see this tabular column, you can easily understand that the Pelton turbine is an impulse turbine. They are using kinetic energy. The head is high head turbine, that is more than 250-meter height is being used. Discharge is low. It is a tangential flow turbine, and specific speed is low. Whereas for the uh, Francis and the Kepler turbines, both are reaction turbines. Both are uses kinetic as well as the pressure energy. Medium and low head can be used. Francis is used for medium head, and Kepler is used for low head. And Francis uses medium discharge, and Kepler uses high discharge. The Francis turbine, they uses a radial flow as well as the mixed flow. The Kepler turbine is only an axial flow. The specific speed for the Francis turbine, it is medium, and Kepler turbine, it is high. So high specific speed turbine is a Kepler turbine from this. Okay, I hope that you have very cleared about the turbines. Next is an impulse turbine, which converts the total head of incoming fluid is converted into a large velocity head. That is, the pressure energy is converted into kinetic energy by means of a nozzle. The nozzle is putting a stream, a high velocity stream on the turbine blade, and the impact, by means of the impact, it will get a run. So the working principle is clearly given in the diagram manner. In the reaction turbine, first we are going to discuss about the Francis turbine. The Francis turbine is generally having a fixed blades as well as the moving blades. The fixed blade converts a part of pressure energy into kinetic energy, and the water entering the runner, that is the moving blade of the reaction turbine, has both pressure as well as the kinetic energies. So here it is. In the Francis turbine, the main problem is cavitation. The cavitation means a conversion of the jet of water into water vapor because of the pressure difference. There here, the cavitation is caused by vapor pressure. This vapor is not at all produced by means of a temperature, it is produced by means of the variation of pressure. So the cavitation is a problem here. The turbines cavitation is at entry position. Turbine, it is in the exit position, where pump is in the entry position. Next is a Kepler turbine. So Kepler turbine, the shaft power displacing the water axially and creating axial thrust in the turbine. Water flows axially and creates axial force on the turbine blades, and this is how it is worked. So this is an axial flow reaction turbine, that is Kepler turbine. In reaction turbines, we are using both pressure as well as the kinetic heads, whereas in the Pelton turbine, they are using pure kinetic energy. The pure kinetic energy with a low rate of flow, and it is having in the impulse turbine, it is not at all having a draft tube for converting all the kinetic energies into pressure energy, since it is open. Pelton turbines are generally open in the tail race, so it cannot produce any distraction or any floods in the outlet flow, where these reaction turbines uses both pressure as well as the kinetic energy, can create a flood in the outlet pipe. If not, it is made with the draft tube. If the draft tube is there in the reaction turbine, the floods are being controlled. Okay, what is the purpose of draft tube is it converts the kinetic energy of the runner outlet into pressure energy of the draft tube outlet. Since the draft tube it is having an increasing in area, we know that the relationship between the area, pressure and velocity. For your information, I would like to give this in detail. We know that the power is equal to pressure into discharge. Therefore, if discharge is reduced, power is being reduced, whereas the discharge is equal to area into velocity. If this q is directly proportional to area as well as q is directly proportional to velocity, where area is inversely proportional to velocity. Since area increases, velocity is being decreases. When the velocity decreases, the kinetic energy is decreases. We know that the kinetic energy ke is equal to half m v square. If velocity becomes reduced, the kinetic energy is become reduced. And we know that power is equal to pressure into discharge. We know that discharge is equal to area into v. Therefore, p is pressure is inversely proportional to area, and p is inversely proportional to velocity. These two have to be known. Therefore, if area, sorry, I hope this thing I made wrong. So when the velocity decreases, pressure increases. Therefore, we know that area and velocities are also inversely proportional, where pressure is directly proportional to area. So if the area increases, pressure will get increases. That is what the interest about. That is why the draft tubes are having an increasing in area. Therefore, and also draft tubes are immersed in the tail race. Draft tubes are generally immersed in the tail race. So all the kinetic energy is converted into pressure energy. Therefore, the flow at outlet is being smooth as possible. And we have a different types of a draft tubes, that is a straight conical draft tube, elbow type draft tube, and hydrocone or moody spreading draft tube, or hydrocones, like that. The different types of draft tubes is being used. So with this, I'm going to close the today's session. If you have any doubts, please let me know by means of a comment section. I will put another video for clarifying your doubt. If you like the video, please like, share and subscribe. Make it a key with Santhosh for continuous update about the mechanical engineering. I hope you have all enjoyed the session. I would like to once again thank you all. Thank you for the patient listening. Thank you.